This conference will now be recorded.
Welcome back to day 4 of SCADA ICS hacking and security from Hackers Arise. I'm OTW, and I'm back from struggling with a week of COVID. And hopefully I can get through another couple of days of this class. This class is really important, as you know, and I want to get this thing finished for you. I am struggling with my voice, so there might be more breaks in this session than is normal. Excuse me, and there it is again, my voice. So what we're going to do today is that I want to start off by talking about the PLCs. Right? So we've mentioned the PLCs in the past, but I want to spend a little bit of time talking about PLCs and what they are, what they do, who makes them, how they operate, right? And we'll look at some ways of exploiting the PLCs. We'll look at those that are modules that are available on Metasploit and other places. We'll look at some tools for being able to exploit the PLCs, and we'll do it in the real world. All right, so we'll go after the Russians today. We'll see if we can exploit some of those Russian PLCs. Normally that would be a risky endeavor, but not in this environment because they're already after me, right? So I'm not going to piss them off any more than they already pissed off at me. So we're going to do that. And with all that having been said, let's get started. Let's talk about PLCs. Start off with. Okay, basics of PLC. So what we're going to do is just kind of introduce some of the concepts, okay, around these PLCs. I mean, we've been talking about them. We know that they're the heart of these industrial systems. We know a little bit about Modbus. Oh, I also want to throw in that we'll do some Wireshark analysis of Modbus as well today. All right, you should have in the tools, the tools section, you should have a couple of PCAP files, Modbus PCAP files. We'll take a look at those as well, so you can get a better look from a PCAP perspective, the details of Modbus, the Modbus protocol. But let's talk about these PLCs, and this is the ever-present Siemens Cymatic S7 1500, which is yeah, you should have gotten. I sent everybody a link to the tools. You should have had it last week. Okay. Administrator says still no link on email. What does that mean? There's still no link on email. The tools, is that what you're saying, administrator? Okay. Put your email in the chat and I'll send it to you right now. Everybody in class, one of the things I want to continue to emphasize to you is that a lot of my emails end up in your spam folder, and check your spam folder. And I send them out all together. There's 120 some people who are registered for this class, and it goes out to everybody. And if it doesn't appear in your inbox, check your spam folder. Okay. All right. Pablo, here, I'm going to send it out to you right now. Okay. All right. Renegade, so they switched to Proton Mail, Proton ME, and it works fine since then. Good. All right. It's sometimes even Proton will put my emails into spam now. I had a discussion with somebody a couple days ago, and any case, he was irritated that he wasn't getting emails, and he said, I know it's not going into spam because I get your other emails. Okay, well, you know what? I use 3 or 4 different email addresses for different purposes. All right. So the ones that when I have to send out a mass email to like hundreds, like the number who are involved in today's class, I use one email address for that. I use a different email for personal. I use a different email account for members. I use different. So anyways, that's just because you get one of them goes into your inbox doesn't mean that all of them are going to go into your inbox. So make sure you check your spam folder. Okay. All right, let's talk about these PLCs. All right, we'll talk about a little bit of the history of them, the relay ladder logic. So yeah, we'll talk more. Central processing unit, input output system, programming peripheral devices. Okay, programming concepts, applications, troubleshooting and maintenance. All right. So the advantages of the PLCs initially, when people built industrial plants before the PLC, they had to wire everything to a central computer. Imagine building a refinery, right? Or building a large manufacturing plant. You know, the automobile manufacturing plants are huge. I mean, they cover square miles. Okay, they cover square miles, square kilometers, right? Many square kilometers. Imagine having to run a wire, you know, from every point within that facility to a central computer. Okay, that's what used to be the case. The wiring between devices and relay contacts are done in the PLC program now. Okay, easier and faster to make changes, less wiring as well. Troubleshooting aids makes the programming easier and reduces downtime. And then you have reliable components make these likely to operate for years before failure. There goes my voice. So the origins, they're developed to replace relays. Now, when we say relays, we're talking about electromechanical relays. Okay, these are, in the old days, it was basically a relay was an open or closed switch. Okay, and you know, within the industry, there's still this terminology that people talk about coils. Okay, and you'll see that when we get into the next section. People talk about coils, and that's a reference to the old relays that basically was a switch that opened and closed. All right, so a coil is simply what often is referred to as a relay, and it opens and closes. It opens and closes. That's all it does. 0 and 1. Okay, it only has 2 values. It's either open or close. The cost dropped and became very popular in the 1980s after they, remember, Modbus was developed in 1979, now used in many industrial designs. Some of the historical background, Hydromatic, as a General Motors Corporation, specified the criteria for the first programmable controller in 1968. You know, in 1968, General Motors was the largest corporation in the world. Okay, they made the vast majority of cars in the world in 1968. So most of the manufacturing processes and developments in manufacturing in the 60s and 70s was done by General Motors because they were this massive corporation, the largest corporation in the world. Of course, they're much smaller today, now that they have competition. But so they really pioneered the idea of using these relays and the programmable controller to be able to automate the processes in a manufacturing industrial facility. The primary goal was to eliminate the high costs associated with inflexible relay controlled systems. This is 1968, before all of you were born. Maybe some of you were born at that point, but not most of you were not. The controller had to be designed in a modular form, so they specified. They're the ones who specify what this controller should look like and what it should do. Right? So the sub-assemblies could be removed easily for replacement or repair. Good thinking. All right. The control system needed the capability to pass data collection to a central system, and the system had to be reusable. The method used to program the controller had to be simple, so it could be easily understood by plant personnel. Some of the developments, the concept was first developed in 68, 69, the hardware CPU controller with logic, right? So this is actually before the integrated circuit. Okay, so we didn't get integrated circuits till the 70s, right? So this is a CPU that's not an integrated circuit, okay? Had logic instructions, 1K of memory and 128 IO points, right? Use of several multiprocessors within a PLC, timers, counters, or arithmetic operations, 12K of memory. So these are proprietary systems, right, that you couldn't use between different we don't have protocol yet. 1024 IO points by 76. Okay, have remote input output systems introduced. So here we get 77. We get microprocessors based PLC, right? We started getting ICs, getting microprocessors in the 70s and early 70s. In 76 was when the first Apple appeared, right? The IBM computer has not come out until 81, right? So we're getting PLCs that have microprocessors based on them. By 1980, we get intelligent I/O modules, input-output modules are developed, enhanced communication facilities, enhanced software features, use of personal microcomputers. By 1980, still we don't have what we call the Windows machine, all right? We don't have that yet, okay? We have a lot of proprietary operating systems working on, at this point, they're mostly working on Zilog, Z80s, or Motorola chips. By 83, we get low-cost, small PLCs introduced. 85, networking all levels of the PLC, computer and machine using SCADA software. So, definition of PLC, a digitally operating electronic apparatus which uses a programming memory for the internal storage of instructions for implementing specific instructions such as logic, sequencing, timing, counting, and arithmetic to control through digital and analog modules, various types of machines or processes. The top leading brands of PLCs, I updated this the other day, so it should be pretty current. Okay, Siemens is the big boy in this, 30 to 40% of the world's market. German company. They're the manufacturer of the S7 1500 or the Cymatic class. These are the ones that are used by Iran in the uranium enrichment facility at Natanz that Stuxnet attacked. It uses the Profibus class of protocols. They use Profinet, Profibus, okay? Yeah, largely used in manufacturing throughout the world. Rockwell Automation, we were looking at some of theirs. We were attacking some of theirs the other day. This is Rockwell, who purchased Allen Bradley. Once again, largely manufacturing. All right, we saw them being used in a water treatment plant, if I remember correctly, when we were trying to get into their HMI. and they're a major player largely in manufacturing. Okay. And they're headquartered in Milwaukee, Wisconsin, which is kind of the center of the manufacturing industry in the United States. Rockwell's a defense contractor largely, and they purchased Allen Bradley, so it's now often referred to as Rockwell Allen Bradley. Mitsubishi, okay, is Japanese, obviously one of the largest industrial corporations in Japan. They make the Melsec for PLCs used throughout the world. Schneider Electric, my favorite, okay. Schneider is a Paris, France-based company. They purchased Modicon. Okay, Modicon was the company who developed the Modbus protocol in 1979 and made it open source. Okay, and so they purchased it, and they've now purchased a number of different companies. And one of the companies they also own is APC, the UPS developer, the UPS manufacturer, which is an American company. And in all honesty, these guys just don't think about security. I've been dealing with these guys for a long, long time, and they just don't give enough attention to security. They sell a lot of product, and they don't secure their products very well. I'm going to be doing another David Bombal interview here shortly. You'll see it come out, and what we're talking about is hacking the APCs, the uninterruptible power supplies by Schneider Electric. Okay, so we've seen their products here in the SCADA environment that often are insecure, but their APC products are insecure. And just a couple of months ago, a bunch of new vulnerabilities came out on those. And we don't often think about the power supply, the uninterruptible power supply, as a target, okay? But they can be. They are connected to the internet. Many of the what are called smart UPSs are connected to the internet, and in this case, you can actually upgrade the firmware, replace the firmware on them with from remote locations, and put your own code inside of them. All right, so and that's another of the insecure products coming from our friends at Schneider Electric. ABB, Swedish company. Honeywell Process, another American company, American industrial company. Omron, Sysmac, their product line. Hitachi, Japanese. IDEC, and B&R Industrial Automation. Okay, those are the top 10. There's probably well over 100 companies total in this industry. All right, these are the top 10. Areas of application, including manufacturing, machining. So anybody who's making anything, now think about this. Anybody who's making anything has a PLC in their facility, right? Which is a lot of people, right? If you're manufacturing anything, you're machining anything, you've got a PLC in it. A lot of products now are machined, okay, by a machine. So that's all been programmed into a PLC that is cutting a piece of product apart for say a refinery or a manufacturing facility, or putting into an automobile. Food, beverage, okay, once again, one of those areas, Voltage knows this area well, okay. One of his groups, one of the targets of his group was a food processing plant in Russia. So I mean, these guys are also using PLCs, right? Excuse me. Metals, power. So the whole electrical generation and transmission industry uses PLCs. If you talk about power, we're talking about possibly, the entire transmission gas transmission systems are also run by PLCs. Mining, petrochemical, chemical, basically just about anybody, you know, just about any industrial process, you know, we can say everybody who's an industrial process is using a PLC. And that's probably, you know, safe statement to make. I'm sure there are some exceptions to that, but it's pretty safe to say just about everybody is. All right. So to give you some idea of what a PLC does, we're creating a really simple process. All right. A very simple process that needs control, right? It needs control. So here we have a tank, okay? This is a tank, right? And here we have two liquids that have to go into this tank, be mixed, okay? And then these two liquids should only go into this tank until it's full, okay? So we have a float switch. We have a timer that we need to set for how long to stir them. And then we have a solenoid here for the output, right? This is the kind of process that a PLC can do really well, right? I mean, you can think about it, this is a pretty simple process. But we need, you know, we could have a human being sitting there pushing and pulling switches, right? But it's much cheaper to buy a PLC than to put a human being there. And human beings fall asleep at the wheel, what have you, and aren't always reliable, especially if you have a Homer running your plant. All right, here's our tank. The tank's used to mix two liquids, okay? The control circuit operates as follows, okay? When the start button's pressed, okay? This is an input. This is one of the inputs, right? IO, right? When the start button's pressed, solenoids A and B energize, okay? They open up, all right? This permits the two liquids to begin filling the tank. When the tank is filled, the float switch trips. We saw that in the previous diagram. This de-energizes solenoids A and B and starts the motor used by to mix the liquids together. Okay, you can see that the real simple logic that's going on here that we could build into a PLC. The motor is permitted to run for 1 minute. After 1 minute has elapsed, the motor turns off and the solenoid C energizes to drain the tank. When the tank's empty, the float switch de-energizes solenoid C. All right. As the stop button can be used to stop the process at any time. If the motor becomes overloaded, the action of the entire circuit will stop. Once the circuit has been energized, it will continue to operate until it's manually stopped. So just keep on doing it over and over and over again. So some of the major components of a PLC. At the heart of a PLC is the processor, of course. Right? There's got to be a brain there. It's an integrated circuit now. Right? Got to have power. Power to the processor. You got to have a programming device. So we have to have some way to add the programming to the system, right? In modern systems, this is usually done by a laptop with some programming interface, a ladder logic, kind of GUI-based programming logic that we can go ahead and put into. Each one of the manufacturers tends to use their own programming device and interface. We have input modules, of course, and we have output modules. So from the sensors, we get push buttons, contacts, limit switches. These are all going to be in the input modules, feeding data into the processor, which then uses the logic from the programming device to make decisions. And then we have our output module. These include solenoids, contactors, alarms, what have you. So power supply provides the voltage needed to run the primary PLC components. We have I/O modules, provide signal conversion. Now this is something we don't think about, okay? Provide signal conversion and isolation between the internal logic, level signals inside the PLC and the field's high level signals. So the outside signals tend to be higher voltage, right? And then they have to be converted to a lower level to be able to be used by the PLC. Processor provides intelligence to command and govern the activities of the entire PLC systems. We have a programming interface that's used to enter the desired program that will determine the sequence of operation and control of process equipment or driven machine. These programming devices have different names. Different companies use different names for them, but in modern systems, almost everybody is allowing you to download their software onto your laptop and simply use an Ethernet cable to be able to upload your logic to these systems. But they have different names of different companies. One of the things that's, is probably unique among this industry is how proprietary it is. Right? Every company tries really, really hard to be unique and proprietary. So they all have different names for the same products. They have different protocols. They have different PLCs. But there are some unifying elements. And one of the unifying elements is the Modbus protocol. Right? Even though people don't necessarily use it, all right, but they usually have a terminal on the system, an interface, where they can actually connect to Modbus if necessary and communicate over Modbus. So some of the programming device types is there used to be these handheld LED, LCD displays, a desktop, compatible computer terminal. Most people now have gone to a laptop. But once again, if you're working in this industry, you're not necessarily working with the latest and greatest, right? I mean, we've got products that are out there that have come from 1979, right? And if you're working in the industry, you might very well have a 40-year-old product that you have to interface with. And you'll have to use whatever is compatible with that system. The I/O modules, these interface sections of the PLC, connects to external field devices such as temperature gauges, pressure gauges, right? Start and stop buttons. These would be all I/O modules. The main purpose of the I/O interface is to condition the various signals received from or sent to the external input and output devices. Input modules convert signals from discrete or analog input devices to logic levels acceptable to the PLC's controllers, okay? So this is the module that's part of the PLC that takes the inputs from these field devices and converts them into a signal that the PLC can understand. Output modules convert signals from the processor to the levels capable of driving the connected discrete or analog output device. DC input module. We have an opto isolator. So the first step is to drop the voltage to logic level. And then we have an opto isolator, prevents the voltage transients from damaging the processor, helps reduce the effects of electrical noise. We don't want that noise to get to the CPU. Then we have buffer, filters, hysteresis circuits, all before it gets to the processor. The AC input module converts the AC to DC and drops the voltage to logic level. The opto isolator prevents voltage transients from damaging the processor, helps reduce electrical noise. And once again, we have the buffer, filter, and hysteresis circuits. Here's some of our connections. I'm going to go through this part pretty quickly. There's an awful lot of information here. I want you to have a good fundamental understanding of, but you're not going to be a PLC engineer. But if you're attacking these things, you have to have a basic understanding of how they work. I think that's about all I want you to have on PLCs. Give you some basic understanding. CJ says, are the I/O modules and PLCs usually modular? Okay, let's talk a little bit about that. The I/O modules are not necessarily modular. They're unique to that PLC. The PLCs are modular, okay? So they can be connected, okay, and speak to each other. And so you can basically put a whole string of them together. That's part of the concept behind a PLC, is to be able to take these and get them to work together, okay, in a process of, say, manufacturing or what have you. So let's go on and let's take a look now. Okay, so you have a little bit of understanding, hopefully, of what a generic PLC does. I'm gonna exit from here. And what I'd like you to do is to open up the Modbus PCAP file that I sent you, all right, with Wireshark. All right, see, Will says Cali. What does that mean? Are you asking? Let's go with part 1 first. All right, should look something like this. I'll do a full screen for us. You should have two, part 1, part 2. We'll look at both of them. Yeah, it's in the Mello. It's in the Dropbox that I sent you a link. Send everybody a link to. I'll just pause for a moment here, let you all get that going. You can use it either in Windows or in Linux. It doesn't matter. Wireshark works in both. Doug has arrived. Okay. Everybody able to open up our Modbus test data? Chris says yes. Anybody who's not been able to? Sec says yes. Okay, if you've got it open, let's take a look at it. All right. So this, of course, is Wireshark. Hopefully you're familiar with it. You know, we have 3 windows. Up here we have, this is what we're doing here is, you know, when you want to go ahead and view a PCAP file, you can simply go open, right? And then choose the PCAP file and then go ahead and open. And that's what we did. Or if you just click on a PCAP, it'll automatically open Wireshark. Right. So this is Modbus, and if up here we have each of the packets. There's not that many packets in this PCAP. I don't know. There's maybe how many? 118. Pretty small. Right. But once again, you know, the Modbus is a pretty lightweight. Doesn't require a whole lot of communication. Looks like this protocol here is TCP. So we're having communication going on between 10.0057 to 10.003 using TCP, okay? And notice that it's going to MBAP 502, okay? And it's using a fin and an ACK, all right? So What's this mean here? It means, looks like, in this case, 100057 is closing. It's a fin and an ACK. It's closing a connection to port 502. MBAP is the acronym for Modbus. All right, so if we want to go ahead and analyze Modbus, we can go up here and go to Analyze. All right, go to display filter. I had to think a second here. Display filter. Let's go here. All right. And this is display filter expression. This is the way that if you don't know what filter to display, okay, this will help you, guide you through it. All right. And in our case here, we're talking about Modbus. So we're going to have to go down. We could go ahead and put in right in the search right here, go Modbus. All right. And it selects a few. And you can see that the options we have here are the RTU, which is the serial, okay, connection. Here's the TCP, all right? Let's take a look at each one of these, all right? And then these are all the fields that we can use, all right? And then if we go over to Modbus TCP, all we have here is cannot classify, and then we have Modbus UDP here. So really what we want to look at, all right, is this right here, this Modbus. And these are, notice, remember we were talking about all the codes? Remote terminal unit. Okay, Chris asked, what does RTU stand for? Remote terminal unit. All right, so remote terminal unit will run over a serial connection, okay? So here's the variety of fields, okay, that we can use in examining our Modbus. All right. So if we wanted to simply extract the Modbus out of this PCAP, we could just put in Modbus, okay, as our filter. As soon as we complete the word Modbus, you can see it turns green. That means that our filter is accurate. And now we can see these are all Modbus. All the TCP has been extracted, okay, and we filtered just for the Modbus. Now, let's see here. We have packet number 8. You can see it right here. So the first, look at the first 7 packets were TCP. And this one here is coming from this IP address to this destination. The protocol is Modbus TCP. The length is 66. Okay. Now look at here. Function code 8. Okay. Let's go ahead and click on it. All right. So we clicked on that. And then we can go down below here and take a look at that Modbus. Okay, and there's our unit identifier. Okay, remember the unit identifier was the identifier for the PLC, right? And then if we can open up down here, all right, we can go and we can see function code 8. Okay, and then subcode 4. All right, subcode 4 is force listen open only. It's a DOS attack. All right. So this will take the PLC and it'll tell it not to respond. Okay, force listen open. It's a diagnostic code. It was used in a number of DOS attacks. Let's take a look at some of these others. Now here's the response from that same PLC. Let's see how it responds. It comes back with, once again, unit identifier 10, okay, function code 8, diagnostics, okay, gateway target device failed to respond, right? And so it's throwing an exception code, the gateway target device failed to respond. Here's exception diagnostic code 8. Let's go through each one. So looks like they're continuing to try to do a forceless and open DOS attack. So if I can go ahead and go to each one of the units, it looks like here, let's go through, they're going always targeting, okay, they're always targeting unit 10, all right? But it looks like here, return exception, forceless and open. So it looks like at this point, okay, they're then going to here, let's go restart communication option, all right? So over here, we can see the diagnostic code 8, restart communication option 1, all right? You see that's been, they do that several times. And then in this one here, remember these are really, really lightweight communications, very simple communications. Administrator says, can we somehow use the request example from here to use it on a real controller? Well, that's what we're going to do next. Okay, so yes, the answer is yes. We will use these in against some Russian PLCs. Right? I mean, well, we're going to test to see whether or not those Russians are securing their PLCs adequately. But yes, so here's what they're doing here. This is an attacker, okay, and they've restarted communication. Now let's talk about attacking PLCs or attacking SCADA ICS. There's at least two ways of attacking. SCADA ICS. Okay, one is to attack the protocol. All right, this is what we're looking at right here is attacking the protocol. What we're doing is we know what the vulnerabilities are in this protocol. We know how to send packets into the PLC that will cause havoc within the PLC. That's what this is. This is an actual attack against a PLC. All right, and I'll show you how to do this in just a little bit. Of course, you can also do a replay attack. Just use this and replay it, assuming you can get into port 502, right? But so this is all goes back to what we were doing, I think, in day 2, where I showed you the codes of Modbus. Okay, each one of the protocols are a little bit different. Right? So this is just Modbus. This only works in Modbus. Right? But Modbus is the most widely used. So once they've done is they've forced listen open, then they go and start communication option, restart communication option, which you can see there. Okay, we got it clicked here. It is function code 8. Okay, restart communication option 1. That's subcode 1. And there's like 4 packets there. And then over here, we have function code 8. Okay, and now it's clear counters and diagnostic register. Okay, so what we're doing is we're clearing all the counters on the PLC and the diagnostic register. And that's, you see multiple packets going here for that purposes. Then read device identification. Okay, this is going to be function code 43. All right, so here is function code, encapsulated interface transport, function code 43, read device identification, read device ID, okay, object ID, product code 1. All right, you see these 2 packets communicating here. Then we have a report slave ID. This is function code 17. Right? So an attack against the protocol requires that you have a pretty good understanding of what's going on in these simple protocol of Modbus. All right. Here's all the reports on the slaves. Okay, they're going ahead and doing reporting on the slaves. And then here, read coils. Here's that terminology that I was referring to. So in SCADA ICS, when you see the term coil, basically what they're talking about is an on-off switch. So it could be very well be a button, okay? It could be a valve opening and closing. These are usually referred to as coils. And it comes from the old days, the electrical mechanical days. So the industry still uses this terminology of coils, which is an open closed switch, electrical mechanical switch. So remember that the protocol was written from that era, right? It was written during that era, so it uses that terminology. Renegade says, can we hack Snickers to put more nuts into their bar? Yes, we could, but some of us would prefer less nuts into the bars. So you're on your own on that one. So here's read coils. Now notice here it's gone to function code number 1. All right. It's reading the coil. So what this is doing is it's going ahead, it's going ahead and pulling the data off the coil. Meaning, is it saying, are you open or are you closed? Are you open or are you closed? Now, this would be a reconnaissance phase now. So what we're trying to do is trying to understand, what that particular coil is doing. What state is it in? Is it in open or closed? All right. And then after that, we go into read holding registers. Okay. All right, so this is going to be function code 3. Okay. Read holding registers. The holding registers are a memory area that has values in it, such as, how many seconds should I stir the liquid? Remember from our PLC, right? So I've got to hold somewhere a value that says how long should I turn that motor, okay, to stir that liquid. That would be in a holding register. Now we started getting into more malicious stuff. So this has been all reconnaissance here, right? Then we get into write single coil. This is going to be function code 5, all right? Write single coil. Write single coil. These are all writing coils. And then we're writing a register. This is function code 6, right here. You can see it right here, function code 6. So now we're beginning to put values into the PLC. All right, so we've gone ahead, we've done a reconnaissance, we've seen what the values are. Of course, those values are going to change, right? So remember, it's going through a ladder logic, right? So it's going through a ladder logic, and as going through the ladder logic, it's going ahead and changing. So a coil will be open, closed, open, closed, open, closed, okay? Usually the registers, they will change as well, but they are more stable values than you'll see in the coils, okay? Because you're not going to change the number of seconds that you're going to stir the liquid. Okay, that's going to usually be a fixed value. But if I can change that value, all right, I might be able to raise havoc with that system. So for instance, if the two liquids had to be stirred to a certain extent to make them effective in the next phase, okay, of the manufacturing process, if I were to cut back the stirring from 60 seconds to 1 second, what's going to happen when that liquid that's not fully homogenized goes to the next level? Well, we don't know. We don't know what the process is, but it's not ideal. It's less than optimal, right? Because the programmer has put in the logic that is considered to be optimal. If you start changing these values, you don't know what the outcome's going to be, but it's less than optimal. We can say that. It's less than optimal, right? And so here we are, started writing some values, okay, into those registers. believe it or not, okay, believe it or not, there are systems around the world where you can still do this from the outside of these systems, right? And then here we go ahead and read coils again. And then it has returns an unknown function, function 42. So they put in a function that is not it's not recognized by the system. Okay, let's take a look at another one. All right, let's see. I have two of them in there. Let's look at one more. And we're going to do exactly these actions in just a moment. Okay, I'm downloading that. The next Modbus Part 2 should be up on the screen here. Here it comes. Okay. So we can see there's some bad TCP in here. All right. Also note, oh, and voltage has some of his own as well. It says new Wireshark fails to load your PCAPs. Okay. These are relatively old. I'm using a new version of Wireshark. I haven't updated it in say the last year or so. So maybe the new ones. It did not update mine. Yeah, mine's not updated. Mine's probably a year old. So maybe the brand new ones won't work. But let's take a look at these. We have what 350 packets here. All right. Okay, no problem. Nephos has no problems with his. He's all updated. I'm not sure what the potential problems are here, but let's go through these packets and do our little Wireshark analysis. Okay, this would be, if we were, say, a security engineer, right, and we had a sniffer at port 502, right? So, which would maybe be a good idea, to put something in there to be able to analyze the packets coming into port 502. But what we've seen is that that's not the case, okay? So this is basically looking at the traffic coming in. It's all coming into port 502. That's Modbus's default port. These are some bad packets here. This is the TCP transmission. Okay, something happened en route, had to retransmit it, got lost, what have you. All right, looks like from this IP address to this IP address on MBAP is the way that Wireshark designates Modbus port 502. All right, and then it's opening up a SYN ACK. Right, next packet is an ACK on port 502 Modbus. And then, but this is all TCP. This is the connection. Right? This is an initial connection going on here. Then Modbus starts here. Okay. We have one more TCP packet. Another one here. These are all ACK packets. Modbus again. Comes back with an unknown function, exception returned. TCP again. Modbus. And they're beginning to read coils here. All right, let's take a look at what's going on here. All right. So unit identifier, they're going after unit identifier 1. All right. And the function code is number 1, read coils. And more read coils. This came back with exception return. There was a problem. Looks like it came back with an error message and trying to read the coils. Read discrete inputs. Came back with an exception. read the registers, came back with an exception. So they're going through and trying to find as much information as they can. Read input registers. Looks like each one of them failed. All right. Then we go to, okay, great voltage. Okay, might be a little bit different than ours. Okay, but in any case, you get the idea here is to get a feel for what Modbus looks like from a Wireshark, from a security engineer's perspective, right? What does it look like when somebody's trying to attack? Or in some cases, this might be a somebody, if it's one of our people, right? If it's one of our people, this might be somebody who's just trying to control the PLCs, right? If it's one of our people. If it's not one of our people, if it's outside of our network or outside of our whitelist, this could be the signs of an attack. And if somebody from the outside is trying to write to your system, you've got a problem, right? Houston, you have a problem. So it looks like writing the single coil worked. Then they tried to write a single register and they got an exception returned. Here's another TCP packet here. Here's read the exception status, right? So let's go, this is going to be, let's go down here and take a look at, it's going to be read exception status. It's going to be function code 7, right? And here's once again another read exception, return query data. This is function code 8. Function code 8 is all diagnostics, okay? Voltage says rapid SCADA would have different packet naming protocol. Yes, once again, there's that whole proprietary nature, that everybody's using. So it's likely to be slightly different depending upon. Rapid SCADA can be used in multiple environments. So it depends upon what environment they're using. It's also true that Schneider Electric has what they call Modbus Plus, okay? And they use the same basic function codes, but they add additional function codes, okay, that only work on their systems. All right, so, okay, hopefully I answered those questions. The return query data, here's an unknown function, function 9. Function 9 is not a workable function. Here's some getting communication event counters. This throws a exception. So these don't work either. Unknown function 13. Looks like this might be a script that somebody is just running through, testing each one of the functions out to see which ones will work and which ones won't. And it's, because anybody who knew what they were doing would not try function 13 or function 9 because these are unknown functions. They're not workable functions within a Modbus. And then here we get writing multiple coils. Okay, I'm trying to write multiple coils. Here we get it's function code 15. So it allows us, we can write multiple coils simultaneously, okay, with function code 15. But we get an exception returned. Try it again. Here, this one's asking us to report slave ID, function code 17. This is essentially what we were sending out. Remember when we were trying to identify all the slave IDs, right? And they would respond with their unit IDs. That's what we were sending to them. Report slave ID. Tell me what your ID number is, right? More unknown functions. Read file record. Okay, this is function code 20. Write file record. mask right. In this case, read file is the, oftentimes in many of the PLCs, this is the file that will contain the ladder logic, all right? And so when we get into the next section, I'll show you what's going on here. And that until recent years, okay, in many of these things, you could just download, okay, and read their ladder logic, all right? And you see some of the other function codes. We can just, looks like this particular attack, it looks like somebody was just going through and trying out each one of the function codes to see which ones they could get to work. It may have been a script that just went through function codes. You can see it's going through 31, 32, 33. These are all, function codes that are not functional in Modbus. So it's a script that says, okay, let's go through all the potential function codes and see which ones I can get to work. And of course, after I know which ones, yes, this could be like a fingerprinting of a system, right? And remember that in Schneider, they have, even though these are not known functions in standard Modbus, Schneider adds some function codes in their Modbus Plus, okay? So this might be a good tactic to learn and see whether or not it's actually Modbus Plus and see what other function codes might be working. So it looks like this is a script to just go through all of the potential function codes, right, to see which ones actually work and which ones don't. Yeah, so it's just going through each one of the function code numbers, see, and coming back with exceptions. Let me throw up on the screen for you again the function codes in Modbus, so you can kind of get a feel for now that you're seeing them in action. All right, give me a second, and I'll give you the table of function codes in Modbus. Mello asks, is there anything different between Modbus and Modbus Plus besides codes? Well, that's all there is codes. So if you're asking me, is there anything else different between it? The only difference between these is the codes, right? The codes are everything, right? The codes are all the communication in Modbus is through codes, right? So is that all there is? Well, that's all Modbus is codes and subcodes, right? And a small area for data to be. I'm going to get you a table here. There's not much more to Modbus than just codes. That's all the communication that they're doing. All right, I'm going to get you. Hey, Nick's here. Welcome, Nick. I know I have a table of Modbus codes. I'll get it for you here. Here it is. All right, here's some of them. Okay. I got some of the others as well. Okay. So 00 return query data, 01 restart communication option. We saw that, okay, in that Wireshark PCAP, return diagnostic register, change the ASCII delimiter. These are actually subcodes of 8. Let's go ahead and let's go and put this one up. I'm gonna expand this one. Here's some of them that we saw. These are the first 8, and these are probably the most important ones. Okay, read coils, we saw that one. Read discrete inputs, read holding registers, we saw that. Read input register, write a single coil, write a single register, read exception status, we saw that. And diagnostic's important because it includes subcode 4, which can be used to stop a PLC, essentially, right? And so, and then these are the subcodes of code Okay, enforce, listen, open is was one of the first attacks against Modbus. So early on, we started seeing attacks against. This was early on was used to I could just stop the PLCs. And of course, once I stopped the PLCs, um, who knows what's going to happen? The whole system is going to fall apart at that point. All right. So there's one more diagram since we're talking about all of this Modbus stuff. Here's a difference between we showed you this the other day, but kind of refresh you now that you have to take a look at it. Here's the simple RTU message. This is the serial. This is the Modbus as it's traversing between PLC to PLC. Right? It's a simple slave ID function code, right? Data, and then a CRC. Just basically check to see if there's any errors. That's all there is. That's it. Nothing more. Pretty simple. So when you say, is that the only difference? Well, the only thing that can be different is function codes and data. Right? That's all there is to this. It's very lightweight. Okay, very simple. When you go ahead and you start sending it over TCP, then it gets encapsulated, right? So you can see the data gets transferred down, becomes known as, and then includes the length, the protocol ID, which simply identifies it as Modbus, and then a transaction ID. That's all it adds to it, okay? So it's still pretty simple packet, even after it's been encapsulated for what is often referred to as MBAP, okay, or Modbus, all right? Okay, let's go ahead and take, administrator says, I have a Russian Modbus PLC we can attack. Okay, well, we'll get to that. Let's take a 15-minute break. I'll give my voice a little bit of chance to rest, take a throat lozenge, and we'll get to do some attacking for research and educational purposes only. Normally I say that, but in this case, I have malicious intent. And I don't care, So if it was, and normally I would say no, it's educational research purposes, but this is the Russians, right? I mean, they have malicious intent, and so I'm returning the malicious intent, and I don't think I can irritate them more than I've already irritated them. So I've got 14 minutes after. Uh, Voltage says I found it. Well, good for you. That's one of mine. So, Voltage says I found Occupy the Web. Actually, you know what? I put my name on several cameras that I've hacked in Russia, and in some of them I've hacked in Ukraine as well. But I've found that somebody else is using my name too, so it may not be me. All right. So usually when I hack a camera, I leave behind my username on it just to let people know that I hacked it. But I found somebody else is using my name as well. So they're hacking, and it might be Russians because I'm going in, I'm hacking, and then the next day I come back and I can't get into that camera, and all the language has been reversed from English to Russian. And so I'm not, and they're using my name when they're going in there. So it may not be me, it may be me, but I've left my name behind on many of those cameras. Okay. FYI, camera hacking is one of the most important kinds of hacks, even though it may not seem like it. Thank you. I appreciate that. Okay. I think right now it's pretty important for us to keep an eye on what the Russians are doing, or what they may do, and if nothing else, by keeping their cameras, okay, but keeping these cameras and letting them know we have the cameras, we're warning them that you are on camera. If you commit the atrocities that you've committed in this war already, that we will have your face. That's the main reason for hacking those cameras. And that's why I've hacked mostly Ukrainian cameras. I hacked some Russian cameras as well. But I want the Russians to know, you come into this city, okay, and I've got them in many of the cities that are on the front lines. You come into the city, you start creating atrocities in the streets, I'm going to have you on camera, okay? Good. All right. I'm glad to hear that. Voltage says, he says, I can't say what or why, but last night I submitted a report to the Ukraine government about some cameras that was so important. I was sent directly to the Ministry of Defense this morning. Congratulations. That's great. And it'll save hundreds of soldiers' lives. All right. Good deal, guys. Okay. I don't underestimate. I think the cameras are really important. Some people, other people might downplay it. I don't. So I've talked a little bit longer than I expected. 17 after, let's come back at 32 after. Okay, give my voice a chance to rest, and we'll come back and we'll try using some of these Modbus packets against some Russian systems. See you then.
This conference will now be recorded.
Okay, we're back. When we left off, we were looking at some of these Wireshark captures, right? These PCAPs of Modbus TCP. These are largely, this looks like a fingerprinting. The other one was it was a DOS attack against a Modbus facility. And so what I want to do now is do the same thing, all right, against some Russian facilities. Okay. We're going to need our Kali. Also, before we go forward, I can tell that my voice isn't going to last much longer. Okay, it's already getting very sore and scratchy. So I'm going to limit today's class to 3 hours to save my voice. We'll come back tomorrow. And this class is so important that I want to probably add a 6th session then. So we'll see how things go. But if I can't get through everything, we'll add a 6th session and do that, because I don't think my voice, I can tell right now, my voice is not going to hold up for 4 hours here today. It's already getting very sore and scratchy. So time for a cough drop and some water. And let's go to our Kali. All right. Doesn't really matter what version of Kali you're working with. They're all going to work just fine for what we're doing here. So let's go ahead and here it is. This is 2022. That's unusual for me to be using such a new version. Okay. But if I don't use a new version, people go, gosh, OTW, why are you using such an old version? Well, because it works. It does what I want. Chris, I use multiple. You can see I've got a 2019 right here, 2020 right here. I use multiple Kalis for different purposes, depending upon what I'm doing. Okay. For class, I try to use a relatively current one. What I did here, this is I just did search exploit on SCADA to find some SCADA exploits. These are basically, when you go search exploit, you're basically searching the exploit DB, right? So we got quite a few modules. Also, later on in class, we'll go through some of the Metasploit modules, but these are just the ones that have the word SCADA in them. So you got to be careful when you're searching for modules. They may not have the word SCADA in ICS. They often will have, say, the name of the company, right? Like GE or Codisys here. So, but I do like the 2019 version, Chris. There are some drawbacks to using it, but so what we want to do next is we want to buy some Russian facilities. I'm going to go ahead and bring in our Shodan IO. All right. And so we can just go port 502, and let's go country RU. The administrator's got one for me, right? But here I've got 2,135 that have port 502 open. Doesn't mean that's a Schneider Electric. It doesn't mean a Modbus, but it has port 502 open. They probably are, especially if they've got these slave IDs in their banners. They probably are. If you go to Hackers Arise, I created a list. There's an Excel spreadsheet that has, I think 370 Schneider Electric facilities that I identified, and I've got the city, the IP address, and the GPS coordinates for all of them. So you can see some of these have here's a Hikvision IP camera, and there's other things that are running on that port 502. But administrator's got one he really wants us to try, so we'll do that. But before we do that, okay, we're going to have to download a tool. All right, and it's going to be, there's a tool known as the Modbus CLI that we're going to have to download. Let me just get you the URL. Let me get that for you. Okay. So I'll leave this on the screen, open up another terminal. And we're going to need to get this tool, we're going to go sudo gem install modbus CLI. And it looks like mine's already installed. Imagine that. Oh, actually, maybe it didn't. Yes, maybe it didn't have it installed in the system. Successfully installed it. Okay. So, all right. Let's go ahead and go modbus and dash help. Pretty simple. It looks pretty simple, at least. All right. So here's the usage modbus options sub command arguments. All right. So the parameters are going to be subcommand arguments. Two is that we want to go ahead and try to read and write those coils on those facilities, similar to what we just saw in those Wireshark captures, right? All right, so we're going to be trying to do exactly the same thing we saw in those Wireshark. One of the things that you need to know is the way that Modbus and Schneider go ahead and name their the memory areas and the addresses of their PLCs. I'm going to throw this up on the screen for you in just a minute. Give me a sec. All right, so here's two things that we need to know. All right, so first of all, let me expand this for you. All right, so this, the data type is a word. Can you guys hear me, by the way? Just make sure I'm getting some messages that you're having some audio issues. All right. Data type's a word. If it's 16 bits, the Schneider address is going to be, starts with a percentage sign, MW100. The Modicon address is 40010.101. And the parameter is going to be word. And you can see the others. So We're going to use a similar terminology for both the word and the integer. There's 16 bits. If we're going to do a floating point, it's going to be MF. If it's going to be a double word, it's going to be MD. And if it's going to be Boolean, the coils, okay, remember coils are simply on or off, percent M100 or just 101 in emoticon. This particular tool should work with both types of addresses, both the Schneider address and the emoticon address. So the emoticon address is the one that is part of the open source specification of emoticon, and Schneider uses, of course, but they try to use a proprietary address. But what we're going to do is we're going to go in and see whether or not we can read and write some of these PLCs in these Russian facilities. All right. All right. So let's go ahead and give it a shot. All right. And the syntax is simply going to be Modbus. All right. And then let's try read first. And let's see, administrator has an IP address for us. Let me check. Okay. 93 187 190 117. Okay, before I go any further, what is this facility? Do you know? Before I put my life on the line. it's not the Kremlin. Geolocate. Okay. It's a nuclear facility. Okay. Any case, let's go ahead and see if we can't pull some data off it. All right. So that's the Schneider Electric terminology, MW. Okay. And then we have to tell it how many that we want to, how many, in this case, these are the MW are going to be simply integer fields, right? 16-bit integer fields. How many we're going to go ahead and try to read? These would be memory areas. There we go. All right. So what we've done is to go inside and begin to read the memory areas on this particular facility. All right. So we've read just the first 10. All right. Oftentimes when you're doing this, you know, if somebody's paying attention, it'll start blocking us, but we'll keep on going until they block us. All right. Sometimes they won't do anything at all. All right. Mello says, wait, you didn't need to log in? No. Okay, I didn't need to log in. I can send Modbus into these Modbus packets into port 502 without logging in. Here, I'm gonna try doing 100. All right, so I got 100 of them. It looks like all of them are either zeros or 700 or 1600. Voltage says I get socket error, no address associated with host name. Anybody else get that? Worked for you? Okay, let's see if I can figure out what caused that. It says, isn't this command showing us not the first 10, but the first 10 starting with from 100? Yeah, from that memory area right there, from that address area. That's the first address area though, okay? So the values seem to be repeating here, 700. This is almost exactly what we saw was being done in our Wireshark PCAPs. Okay, we're going to try using the Modicon, and same thing. Perfect, works great. All right. Now, let's go ahead and go Modbus. Once again, this is in the middle of a war. Okay. By the way, what city is this in? Anybody? Anybody know what city this is in? Petersburg. Okay, St. Petersburg. Okay, St. Petersburg. Then let's go read and go help. Okay. So we're not writing yet. We're just reading. Okay. So what we've done is simply use the host IP account, the number of data to read. All right. Some of the options include the word, integer, dword, float, Modicon, use Modicon addressing, which we've been doing, Schneider addressing, -s is use a slave ID. So it's defaulting to slave ID 1, all right? So we can go ahead and change that, the slave ID, all right? It's defaulting to using port 502, which is a good idea, okay? We can also write the output to a file. So if we're doing reconnaissance on this facility, right, we can go ahead and output this to a file for analysis. It says also a timeout, specify the timeout in seconds when talking to the slave, okay? And so let's continue and let's try some more, all right? Let's try reading the values off the coils, all right? So when we're using the MW, we're using memory areas that we're reading from. Let's go ahead and try reading off the coils. And so that will tell us what coils are on and which ones are off, all right? Let's go using the 101, which is the Modicon. Let's just go 10. So we'll just read 10 coils off slave ID 1, okay? So all we're doing is just reading one slave. And it crapped out on us, okay? Let's see if we can figure out why it's doing that. This often, okay, you'll get this sometimes when they start blocking you, okay? It says the data address received in the query is not an allowable address for the server, okay? Let's try using Schneider and see if that's the problem, okay? Using Schneider address. Sometimes though, when they detect you're probing them, you'll get this kind of error message. I've gotten it many times. And sometimes it's just an error in your syntax too. Let's try using the Schneider address for the coils. Yeah, did it. Okay. But I use the MW. All right. So that's not the coils, that's a memory area. I need to use M. Okay, 100. Let's try that. Yeah. Yeah, so for the coils, we're getting error messages. Let's try some of the other memory areas. Let's try, say, the floating point and see if we can determine what's causing our errors. We'll try different techniques. All right, that's floating point. All right, and then so we're doing well in terms of getting data off. There you go. There's the double words coming off them. Okay. Once again, we're seeing a pattern on these. Okay. I want to get those coils though. All right, so let's see if we can't. Let's try some different techniques that get those coils. Usually the coils are among the easiest to get, but we're definitely getting data off the memory areas. All right. So let's try for the coils we tried 101. I think that crapped out on us. Yeah. Let's try M100. Okay, let's go back to our help screen. Okay, so your administrator is you're getting the, let's go, he says he's using, is this what you're using? Like that? Ah, good deal. Okay, now we're getting the coils. All right, you can see they're just zeros and ones. Thank you for that, administrator. And we could go 100. 100 craps out for some reason. Let's see if we can read 20. Huh. If everybody's targeting the same system, looks like maybe we've only got 10 coils here. All right. Now, let's go ahead. If we're all hitting at the same time, somebody's likely to notice, although not necessarily. Okay. Let's go back to our Modbus read help. All right. So we slave IDs, which would be different PLCs, right? Slave, and then we'll just go in with 2. Okay. I put it in the wrong place. Illegal address slave. Forgot what the syntax is. Let's try it like that. Too many arguments. I've forgotten where the slave goes. Okay, let me try it right here. Slave 2. There we go. Okay. So we got to get the slave ID before the IP address. All right. And so we can see that we for slave number 1, okay, we at least have one coil was open. Okay, slave number 2, they were all closed. Let's see if we can get 100 of them from there. Nope, doesn't like that. Looks like there's very limited number of coils. Let's try 20. And we're just doing recon on this system. All right. No, looks like it only will give us 10. 10's good. 11. Yeah, 11 works. So we're kind of enumerating how many coils there are. 12 looks like it's going to crap out. Yep. Okay. So we know there's got 11 coils there. Okay. Let's go and try the next. Are we all hitting the same system at the same time, you guys? All right, slave number 3. Let's go and see what we can find there. All zeros. Go to the next one. Slave 4. Looks like slave 4 may be gone. Let's remember that we have a tool in Metasploit. Okay, let's open up that. And remember there's a tool in Metasploit that we can go ahead and enumerate, okay, all of the slave IDs. So let's go MSF console here. Chris says, I'm enumerating their login page. Good. All right. I think we should get a little closer to Putin. Maybe just find the next IP address that's in Moscow. Just to piss him off. It's a possibility. There's about, what, 9-10 hour difference between where I'm at and them, depending on where you're at. Okay, that means like right now it is what is it, like 8-9 o'clock at night? So let's go search Modbus. Usually these systems though run 24 hours a day. You know, that's so if you were using it in a manufacturing facility, you're using it in a HVAC system, you know, you're not going to turn it off at night. So I'm not sure that's. Remember this one right here, unit ID. Okay, let's go and see if we can enumerate the unit IDs that are actually functional. All right, there, and then we can use that in our Modbus. All right, so we'll go use. There right now, or 8 o'clock? 8 o'clock. Renegade says, okay. Let's get the IP address from here. It's pretty amazing, actually, okay, that, you know, we're doing this, and there's more than one of us are doing this, and nobody's paying attention, all right? So there's nobody. Sometimes you'll see it. It happens, you know, where I'll be in the middle of one of these recons, and all of a sudden, all I'll get is error messages. You know, I'll be working on it, and you know, everything's working great. And then all of a sudden, I get error messages where somebody has decided that my IP address is malicious. Imagine that. And then show options. All right, and so it looks like everything is set properly here, so we can just type run and see if we can enumerate the unit IDs. Okay, there's station 1, 2, 3. So you can see these are all coming back correct. Okay, so it's telling us that set our host. Yeah, did I set it correctly? Or are you telling me I did it wrong? What's that message? You could be either set our host or our host, either way. Okay, both work. And we could sit there and wait for all of them to go through. And occasionally, most of them will go all the way up to 254, right? And then they'll stop because that's the maximum number, okay? And sometimes they'll go only as high as 242, as administrator points out. The theoretical maximum is 254. In some of the systems, you only go to 242. I'm going to go ahead and do a Control C. It looks like these are all all functioning. And let's go back. Here. Okay, we're reading from the system. Okay, let's control this one. Yeah, it's 254 is the theoretical maximum, but you're right. Oftentimes, you know, though, you'll see that the systems only go to 242. I've seen a lot of systems only go to 242, but theoretical maximum is 254. All right, so let's keep on going through our slaves. Let's see what we can find. There we go. That slave 5 works fine. Slave 4 did not work. All right, slave 5 works fine. Now what we're doing is we're simply going through the coils though, right? That's all we're doing. It looks like slave 6 may not be responding to us. All right, that one, slave 6 did not work. Slave 7. All right, so let's go back to our slave 1. All right, look at those values there. Uh-oh. Somebody may have detected us because it's not, slave 1 is not working right now. Let's try slave 2. Okay, slave 2 is still responding. If we're all hitting at the same time, you know, it's possible that it's crapping out because we're just too much activity on it, right? Essentially, we're DOSing it, right? Too many of us hitting at the same time. Yeah, it's a class DOS. That's what we're doing. So if it won't respond, it maybe if all of us hitting the same slave number 1, same time, it's not going to respond, and we're going to get this kind of error message like we see right here. Okay, so that's reading, all right? How about writing? But before we go to writing, let's just go and try to read, okay, the data values, okay, on that slave 2. Okay, we got all zeros there, okay? Yeah, if all of us are trying to hit the same one at the same time, that's going to cause problems. And if not, anything's going to raise alarm bells, you know, in St. Petersburg is, you know, 20, 30, 40 of us, or whatever there is, 33 of us all hitting the same IP address simultaneously. There's going to be, you know, Igor is going to be upset. So let's go ahead and we've no slave 2 is active. Okay, we got all zeros on there. Let's see if we can change some of the values. So what we've done at this point is basically a recon, right? A fingerprinting of the, and we would want to do this effectively, we'd want to go through all of the slaves, okay, and get all of the values, right? That's, then we would have a good idea of what's going on inside this facility. And did we ever find out what this facility does? I mean, you guys were joking it was a nuclear facility. Is that correct? Is it really a nuclear facility in St. Petersburg? Oh, you were just joking. Okay. What does it say on, it's a telecom. Okay, telecom company. So basically everybody in industry uses these PLCs now. Just about everybody does. So let's go ahead now and see if we can't go ahead and do some writing. Now that's malicious, okay? Because once you can change the values, then you can change the way the system works, right? So the way to do that is go Modbus, okay? And it's going to be a write instead of read. The IP address. Let's use the slave 2. We know slave 2 is working well, okay? So let's continue to work with slave 2. And then we'll go 93, 187, 190. Yeah, let me do the attacking here. 1, it keeps you safe, okay? 2, you can always do this after class, right? And then, you know, it'll keep these guys busy for the rest of the day trying to figure out what's happening. Okay, so we're gonna go and try to write, okay? And then we're gonna write to, let's try writing to the coils first. All right, see if we can just put some 1s in there. And let's go M0 and then 1, 2, gotta put spaces between them. We're just going to change them from from off to on. That's all we're going to do. Now remember that in Modbus, you have to put in values contiguously. Right? It doesn't have this ability to be able to go to a memory area and specify a particular memory area. So you got to start at a starting memory space and then fill in the values of each contiguous value there. It's pretty simple and lightweight. So here we've got, okay, here we're looking at the slave 2 here, all right? And we're talking about, in this case here, the coils. So these are all these coils are off. Let's see if we can turn some of them on. And let's go ahead and hit enter. Ooh, that looks good. We didn't get an error message. That's a good thing. So, oh, Pooty, we've got you. Okay. Let's go back and read now. And see if we've changed the values. Look at that. So we've changed the values, okay, on those coils. We've taken those coils from off to on, all right? Here's what we did initially, all right? And we put in what? We put in 6 ones, all right? So 1, 2, 3, 4, 5, 6. Now, it looks like in the operation, as I was saying earlier, that the coils open and close as part of the process, right? So some of these changes may not be us, right? And some of them may be us. But we went from all of them being closed to many of them being open. Let's go check again, all right? You can see that the process is running, okay? And they're opening and closing these coils as the values are changing. Let's see if we can go and do some more writing. Okay, let's go and see if we can change all of them to ones, at least temporarily. Okay, let's see, and go, all right. And then let's go back and read them and see if we've changed them all. And we changed most of them. Okay, 2 of them didn't get changed. All right. Now this is very dangerous for this facility. All right, we are messing with the values inside their system. We are unauthenticated. We've done no authentication here, right? And we're going ahead and opening and closing coils within this facility. We don't know what that does, right? But it's not optimal. It is suboptimal because somebody on the outside is just randomly changing the values in there, right? Yeah, tomorrow's news will tell us exactly. We're just changing the values, as we go through. And I can see that they've changed again, okay? Let's see if we can do the same thing for, say, another slave. We've done slave 2, right? And we can just, basically we're just trying to throw some randomness into the system to disrupt its smooth operation. That's what we're doing. Which, from a security perspective is a no-no. All right. Okay, that one worked. If it Yeah, I found alarm MP3 sounds very calming. So this is slave number 3. Let's go and read slave number 3 now that we've put the values in and see if we've changed. We were able to change, it looks like 2 of them once again. We were able to get all of them to change except for those 2. And those may be, yeah, another mysterious fire in the RU today, exactly. But we are essentially operating that system. We are changing the values in that. We are opening and closing coils inside that system. We could do this all day long until something breaks, right? Okay. So administrator says, so if we continuously changing this values, for example, via script, we're messing their system. Exactly. That's what we're doing. Their system, these systems, as you can imagine, right? So imagine, think of it as it's a computer program, right? Imagine somebody taking your script and changing the values in your script, randomly, right? You know that script's not going to work right, okay? And that's what we're doing. These systems are designed, so we know that, for instance, in our example, the PLC, that, the motor turns for 1 minute, opens up the valve when it gets, and the valve would be the coil, right? So when we're opening up the solenoid, that's a coil. Closing the solenoid, that's a coil. Well, right now, that's what we're messing with. We're messing with those coils that are opening and closing solenoids to change the values, say, for instance, in how long the motor will turn. That we have to get into the memory areas, the registers. And let's try that next, okay? Somebody picked a really good example. Who picked this? Administrator? This is a good one because, you know, secure systems won't allow you to do this, right? This is a very insecure system, okay? Wow, Chris has got the username and password. Look at that. Okay, go for it, Chris. Go for it. Okay. I mean, you're right there in Norway. You guys have a lot to worry about. Okay, so um, who knows what Putin does next, especially as he gets crazy about, not being successful in Ukraine. He's not a guy who's going to take failure sitting down. And we don't know. I think Poland, Romania, Finland are all easy targets next, and so any case, let's go on and see if we can change some values in the registers. Once again, I mean, we don't know what we're doing, but we know that it's suboptimal. Okay, so let's go ahead and let's try M. We're going to try doing a write. Okay, that's first of all we got to read to know what the values are. Let's do a read, and let's do MW100, okay, for say 10 registers on slave number 3. All right, all zeros. Okay, so what we're going to do is we're going to try to change those. All right, so we're going to go and write to slave number 3. We got to give it the Schneider address, and then let's put in a number that we'll definitely recognize, say 4. Every one will be a 4, and see if we can change the values to 4. All right. Then let's go and read and see if we've changed those values. There they are. You see them? So now we've gone and changed we're at will, we are changing the coils being open or closed, and we're changing the values in memory as well. You know this isn't good. you know this isn't good. You know that this is going to raise problems in the operation of this system. Let's try, let's just mess around with some of the other slaves as well and see what we can do with them. See if it's, sometimes it'll just be one slave you can write to, but that's, that to raise havoc, that may be all that you need is one slave. Let's try number 1. Ah, crapped out on. Is it a chance they detected us? Let's see. Slave number 3 seems to work fine. Let's try slave number 4. Oh, slave 4 works good. All right, let's go and test slave 4 and read it. Isn't it? I hope it's surprising that we can do this in the middle of a war, okay? Even if it wasn't in the middle of a war, you would think that somebody would be paying attention to these these guys, these crazy guys sending data into my system. You can see we're on slave number 4. Okay, we've got voltage is 750. Oh yeah, that's a good point. Voltage 750,000 IT people have fled Russia. There's no one there paying attention. All right. But here on slave 4, we've written values there. These are MW is our integer values. Let's try some larger values in there. Okay. So there's 1,000, 1,001, 1,001, 1,001. All right, let's see if we can send these values into slave 4. All right, no error message. That's usually a sign that worked. Okay. Okay. And let's go back and read. There they are. Okay. So we're just randomly sending shit into their system. All right. And somebody should be paying attention. Maybe somebody is. I don't know. But so far, nothing's happened. Sometimes in the middle of doing this, I'll start getting a bunch of error messages. The MF, we'll try each one of those, the MW, MF, MD values, exactly. And we don't know, notice our 4s are still there too, that we set earlier. Okay, so they're still in place. When the time comes when the values from this slave have to be read, it's going to read 1,001. We don't know what that's going to do, but it's not what it's supposed to be doing. We can be sure of that. All right, so let's try the MF and the MD values, which are bigger values. Okay, all right, and let's actually go to right. Okay, and let's go MF, which is the floating point values. Yeah, control says it's not attacking, it's a special studying session. That's exactly right. It's just like a special military operation. This is a special study session. We're just doing a special study session using Russia as our guinea pig. All right, so let's go and try 2222.22, some floating point numbers. All right, just try out some floating point numbers and see if we can stick them in there. Okay, so this is right to slave 4. Okay, here's our slave 4 right now. All right, let's put in some floating point values. Okay, came back no error. All right, so let's go ahead and read those values, see if they're in there. There they are. All right. Yeah, Modbus slave 4 is crying. Let's try putting it into some of the other slaves and see if we have equal success. All right. Let's just try one again. Okay, one seemed to have a problem. We weren't able to put data into it. Let's try again. Let's see if we can try to put floating point values in. Oh, I put in a read instead of a write. Okay, let me go back up arrow to write. There we go. So we're going to change it to slave number 1. Okay, good. Looks like slave number 1 is going to allow us to. All right, so that was a write. Now we're going to read on that one, and let's go. Yeah, do 10 of them on slave number 1. There they are. So it works on slave number 1. Let's try slave number 2. Heck, let's just go through all the slaves and mess up all their data. All right. Slave number 2. And then we're going to read from slave number 2. There it is. It looks like it's working on all, at least when we're talking about floating point data in these registers, we're getting success on writing to, so far, all of them. And then read. That was slave 2. I should have didn't change the number to slave 3. Let's go slave 3. It's kind of interesting that the numbers that I'm putting in are 222.22. We're getting some errors in there or rounding issues on those numbers, right? Not exactly the 222.22 that I put in. And let's keep going through. Let's do a few more. We know it works on slave 4. Let's try slave 5. And then let's read from slave 5. Putin, you want war? Let me show you what we can do. You underestimated the hackers of the world, Putin. Slave 6 crapped out, okay? Slave 6, either those values aren't going to work or it's not active. Let's try to go to slave 7. Slave 7 is not going to work either. It may be that those after 6 are not functional. Yeah, looks like we can only go through 6. And that may be all that they are using in this operation is just those first 6 slaves. Okay, well, that's one facility. Let's find another one now. Okay, we get an idea. We got this. We're raising some havoc, and nobody's paying any attention because they're not blocking us. But just to check to make sure they aren't blocking us, I mean, it's a possibility we've set off some alarm bells. So let's go back to a slave that we know is working, because sometimes when they start blocking your IP, you'll get messages like this. Okay, so let's go back to slave 4, which we know we were able to attack earlier, and let's try running it again. And if it doesn't work on slave 4, we know that somebody woke up from their nap. Yep, they didn't wake up from their nap. Okay, we're still able to basically exert our will on this facility. All right, we're basically exerting our will. We're putting in whatever we want into these values here. Yeah, they're sleeping tight until the thing blows up. All right, let's go back. I'm going to go back to my Shodan. We'll pick out another random one. Okay, where is my Shodan? All right, right here. Okay, let's get closer to home for Putler. Okay, let's find one in Moscow. Here's Moscow right here. Let's see if we can find something that's like really important to the Russians in Moscow. Let's see if we can find a facility that's, that really should be kept secure, right? Let's see, here's one here. Let's take a look at this. This looks like a web server though. That's probably not Modbus. Okay. Here's an ICS system right here. Let's see what it is. Unit ID 0, that's all it shows. Anybody have any idea what this is? Can track it and see? Let's keep on looking so we can find something it's just obviously, critical infrastructure. If we're doing this, we might as well do some real damage, right? Okay, Shodan. Live target practice for educational purposes. Yeah. All right. This is a DSL access network in the Moscow region. Yeah, we just did a telco. I was looking for something like a military facility or a manufacturing facility, something that we could really, that we might see in the news tomorrow blowing up. No, if you don't specify the slave, it just writes the slave number 1, default slave number 1. Okay, here's something here. Let's take a look at this one. Anybody can read Russian there? Oh yeah, administrator can speak Russian, that's right. Okay. You're in Ukraine. I forgot that. What does this say? Do you know what this means right here? That's this. Oh yeah. It says that's the city right there, Moscow. Yeah, it's like a 8-hour difference. This looks also like a telecom. That's the ISP, but I don't know what that is right there. Port 80 is open, so let's go to port 80 on it and see if we can figure out what it is. It wants me to sign in. Okay. Not going to give me there. I'll just try admin on it, just for kicks. Nope. I'm going to keep on looking. Let's see if we can find something that's really, really important to them. This is all in Moscow. Here's mobile telesystems. JSC RU Center. I don't know what that is. If anybody has a clue, let me know. Yeah, you neither? Okay. Here's a digital network. Here's Inforta telesystem, mobile telesystems there. Yeah, if I can't find something really critical, we'll just grab whatever we can. Looks like that's another telecom. Another telecom. Okay. Let's see. Let's say it's GPRS service at MRFSS. I don't know, that looks important to me. that's, oh, here's a, okay. All right, so here we have port 502. I don't know what this is, if anybody has any idea. Okay. Will says the last system was Segnetics. What is that? I mean, is that something I should know? Segnetics? I don't know who that is. In any case, here's a, there's no other electronics manufacturer in Russia. Okay, then that's probably one we want to go after then. All right, which one was that? What IP is that? If it's electronic manufacturing, let's go attack it. The system that you were previously modifying. Oh, the initial one. The initial one that we were modifying? Oh, good. So we were doing something important. Good. I'm glad to hear that. All right. So I thought somebody said it was a telecom company. Okay. But manufacturing, great. We just messed with their manufacturing process. All right. Let's try this one here. I don't know what this is, but you can tell it only has port 502 open. And usually when it's only port 502 open and you get a slave ID on it, it's usually a manufacturing facility. All right. MRFS says it's a communications telco. What the heck? Let's go ahead and try it anyways. Okay. Let's go ahead and get this IP and use it. This isn't good. Maybe we'll get Putin's telecom. Yeah, right. Exactly. The Shodan shows you who is the telecom ISP, right? And that's where the confusion lie. Okay. So let's go ahead and let's go and test this system, this new system that we just found. Okay. Let's use it here and see if we can get the unit IDs off it. This is using the script that's in Metasploit. All right, and then let's go ahead and go exploit or run. Either way, we'll do the same thing. Okay, it looks good so far. And then it crapped out after, okay, station number 2. All right, that may be all there is 2 stations there. Let's try again. Oh, here this time we're getting more. Okay, so that's a good reason to try more than once. All right, so we only got 2 and then it crapped out. Now we're getting more. There, firewall kicks in. Now here it broke at 6. Sometimes when the firewall kicks in or a security device, you'll get the same kind of error message. So you can't really tell what it is. But let's keep trying and see what we can get. This time it went to 6. Yeah, we got a electronics manufacturing plant in St. Petersburg. This time we got to 7. Okay, yeah, let's try again. And that one might be worth taking the time to just mess with, to write a script, just mess with them constantly, all right? So their whole manufacturing process goes to crap. Okay, here we go. We're up to 10 on this one now. Now we're getting a much better results this time. Persistence pays off. Okay, it crapped out after 20. That's fine. Let's go ahead now and see what we can do to attack it. All right. All right, let's go. Here's our Modbus. All right, let's first start with Let's try doing some reads on it, all right, and see if we can read on this particular device. Read, and then the IP address. All right, and then let's go M0 and read, see if we can read 10 coils. No, crapped out. Okay, let's try MW101. Try reading the registers. Yep. So these guys look like they've got some security in place. This is in Moscow, right? So they're not allowing us to read anything. Let's go MF. Nope. MD. I'm not going to tell you where my VPN endpoint is at. Okay. Yeah, it's just this, there's, I can't control where these videos may end up at, right? So I have to kind of keep some things, I mean, even though it's only us here in class, somebody else takes the videos and shows somebody else, who shows somebody else, who shows somebody else, I don't know where it ends up. So I have to be a little cautious, all right? Let's see. So that one looks like that one is secure, it looks like, all right? Let's try a different one out. Let's see. Let's try this one out here. This one's in Moscow as well. Peter says MD100, not MD101. Thank you. Also, one thing we didn't try when those reads is we didn't try different slaves, okay? And we need to try different slaves. MD. Things like that usually mean. Let's try M, okay, 0. Let's try different slaves. Okay, by default, it goes to slave number 1. Let's try slave number 2. Interregional branch for cell communication. Is that who we're on right now? Is that who we're going after? Let's try MW101. Still not, it's not getting through. Let's try the Modbus terminology. See if that makes a difference. Sometimes it does. No. Let's see if this system is even up. Sometimes systems are taken down after, they appear on Shodan and then they go down for some reason. Let's make sure this one is still up. Yeah, it's up. Okay. And then let's see if port 502 is open, which could also cause a problem for us. If port 502 is not open, and okay, you can see here it's filtered. All right, so we're probably hitting a firewall right there. All right, administrator found another one for us. Good. Let's try that one out. Administrator is very motivated here. He's a Ukrainian. He's got lots of motivation. I think the rest of us are motivated, but not quite as much as the Ukrainians are motivated. All right, let's go. Crapped out. Let's try. It's not working for you, voltage. Okay. Let's try M0 and try slave number 1. Ah, there we go. Okay, so now we got the coils. Okay, good. That's on slave number 1. Let's go to slave number 2. Let's see what we can get. We're getting inside. That's good. All right. We're doing reads. Slave number 2 works. They're all closed. Slave number 3. All right. Good. Okay, these guys looks like we're able to connect to all the slaves. Okay, so far. We're getting, these are all the coils. All right, good. So now let's go see if we can write to these. All right, so in this case, all of these coils are closed. They're all zeros. So let's start doing some reads on them, right? And I'm sorry, some writes. So let's go to, we'll work on slave number 5 and go write, all right? And the only thing we got to do with that is we've got to go ahead and put values in. And of course, on coils, the only value it'll accept is zeros and ones. So just put a bunch of ones in. So we're going to open up all of these. Okay. Peter says it's not better to use SS scan instead of ST to not get detected. You know, all the textbooks say that, right? And so whenever you're sending a packet from Nmap, your IP address is connected to it, right? The only reason the textbooks say that is that if you send an SS, then you don't complete the 3-way handshake so that it doesn't actually get logged, okay? But if there's anything in between, like a firewall or an IDS, anything, it's going to see that the IP address. So you know, I don't buy it that it's more secure, although every textbook says it is. So I mean, if you were spoofing an IP address, that's one thing, but you know, here your IP address is either SS or ST. Your IP address is connected to both of them, right? But every textbook will tell you, oh yeah, SS is a SYN scan or a stealth scan, but you know, it's if there's any kind of security device reading the traffic and logging the traffic that's coming to the system, your IP address is there. All right, let's see if we can do some writing. Okay, looks good. Let's see if we've changed the values here. Oh, what did I do? Oh, I had to change this here. All right, let's go 10. Woohoo! All right. So for one reason or another, it's changed almost all of them except these here. All right. Let's try writing again, see if we can change all of them. Yep, my bad. Let's see, we want to write. Let's write to them. And then let's read them. Ah, crapped out. Read slave 5, 10. There we go. So we're able to write to most of them, but not to all of them. For whatever reason, it may be even that, these just aren't accepting any type of write operations. But we were able to change, what, 7 out of the 10. Let's go and try some of the other slaves and see if we can write to them. You don't have to change much to make these systems go awry. All right. All right, so here's slave 6. And there's the values that are in slave 6 right now. Let's see if we can open up all of these. This one is they're all closed. I'm saying they're all open except for 2. Let's go see if we can open them all. Okay. This is close them all. Slave 6. All right. And let's see if we can close. Okay, I'm going to try to change the first, 6 values to zeros. Parameter count must be positive. I didn't use the parameter count. Interesting. Slave 6, M0. Throwing it in. Oh, thank you. I still have it as, that's the problem. Yep, thank you. That picked it up because it's seeing that as a count value. All right, there you go. Right, thank you. Okay, now let's read. And just to read, and see if we were able to change those first 5. Got to spell read correct. Normally, when I do this exercise in class, I go back and change all the values. In this case, I'm not. All right, we were able to change some of them. Some of them didn't move. All right, so we put in 6 zeros. We were able to change those to zeros. Let's try writing again. See if we can change them. Look at that. We're getting all these 1s now. Let's go ahead and see if we can't put in values in the registers. All right, and let's put in let's do a read on that particular register on slave 6. All right, let's read, say, let's see if we can read 100. Okay, no, how about 10? Nope, doesn't want to let me do that on slave 6. It's possible somebody else is writing as well because we're getting lots of changing values in there. It's also in a normal operation, right? The normal operation values do change, but we saw those were all zeros when we first went there. So it might be somebody else in classes writing values there too. Let's try different slaves here and see what we can get, if we can read. Oh, once again, I'm trying to read. Let's try to read the memory areas, okay, the registers. So we were able to read the okay, let's go back and try the coils. Okay, coils are working fine. All right, let's suggestion to try different addresses. Let's try that. Okay, let's go to MW100s, what Peter's suggesting. Let's see if we can get what we can get there. On slave 3, we're looking at registers. Nope, still craps out. Yeah, it's not allowing us into the registers. It's allowing us into the coils, but not into the registers. All right, and it's allowing us to write the coils. Okay, but we can't even read the registers on this one. Let's try different slaves out. And let's try using see if we can get the floating point data. Sometimes you can't get the integer, but you can get the floating point. Let's try the double word. No. So we're not able to get, looks like the registers here. Control says, does it make sense to rapidly alternate the coils between 0 and 1? If it's a valve or some kind of try to get the stuck halfway open, close. You know, it depends upon the type of facility. All right. Administrator has come up with a suggestion there. Depends upon the facility. And I'm not sure that being stuck between halfway and open and close is going to be any better or worse than just being stuck closed, okay, when it should be open. Right? Okay, let's try Modbus read, and then we'll go MW0 and see what we can get. MW0. Ah, there we go. Thank you very much. Okay. We can see the values there. Let's see if we can get any values for floating point using that terminology. There we go. All right. And how about the double word? Ah, okay. Good deal. All right. So now let's see if we can do some writing to these. All right. Let's go with these double words. Let's try that on slave number 2. Let's make a quick check to see if it works on different slaves. All right. Yep. It's working on all the slaves. All right. So let's go and see if we can write to these slaves. All right. Now let's see. Let's work on slave 4 first. All right. Right. Slave 4. And we got to put in some values here. So I'm going to put in some values that we will note. This is 1, 2, and then we'll do 3, 3, 3. So it looks we're sure that we actually changed them. Okay, so that's just 5 values. So it'd be the first 5 here. Notice that these are double words, so that you can see this is memory address area 0, and then 2, and then 4, and 6, and 8. All right, let's see if we can write these. Woo, I think we got it. All right, let's go and read them. There they are. Nice. All right. Let's just mess with all the slaves then. Since we got it working, let's go and mess with all their slaves. Let's go start slave 1 first. That's right, slave number 2. Ah, slave number 2 didn't work. Slave number 3. slave number 3 worked. Slave number 4 we know works. Let's try slave 5. Let's go do a read on slave 5 now, just to make sure that it's working. Already done successfully. If they fail, that's usually an indication that somebody has slave 2 is still working. Try slave number 3. Yep, slave 3 is working. Okay, I got some let's see, some issues coming up back here. It says taking a break to fix my system, frustrated, hell I'm tired too. Okay, all right, that's what you need to do. Voltage. Okay, you fix it when you come back tomorrow. Control has written a little script there, a little for loop going through, and writing values. Good job. Okay. Oh, you do it. You want me to do it. You're scared. I'm already a target, so it doesn't really matter. Let's reached its limit for today. This was a lot of fun. All right, and we'll keep that. We'll store that little script that you put together. I'll go ahead and copy it. And my voice is starting to lose it. We'll come back and try to do another 3 hours tomorrow. I'll be a little better tomorrow, so we'll try to do another 3 hours tomorrow. And if we don't get through everything, we'll put in a 6th session and do that as well. So hopefully you get the idea that you can go ahead and on many of the systems. I mean, we weren't successful in all of them, but on many of the systems we can both do good recon and then we can put in random values into their PLCs to wreak havoc on these systems. So thanks for coming, guys. We'll see you all tomorrow. We'll see how I feel tomorrow, but right now my throat is starting to give out, and I don't want to stretch it. I don't want to have a setback, and so far so good. And we'll try again tomorrow, same time, same place, and we'll come back to the same place tomorrow. So if you have some targets you want to try, let me know. If you want to spend some time in between now and tomorrow to work on, and we'll try to wreak some more havoc in Russia. All right. Okay. See y'all tomorrow. Thanks for all the good wishes. I'm healing a little bit every day. I'll be a little stronger tomorrow.